When you embed a traditional machine with the capacity to process data, the digital logic and physical components operate as a single unit. The word mechatronics combines mechanism and electronics. This etymology reflects a design philosophy where the boundary between hardware and software is removed. This diagram illustrates how those boundaries overlap, showing the intersection of mechanics, electronics, and information technology. The components on the right, information technology, guided by system theory and automation software, serve as the bridge allowing mechanical parts to communicate with electronic sensors. The purpose is to apply complex decision-making to the operation of physical systems in real time. Mechatronics requires a concurrent engineering approach, where computer logic and physical gears are designed together from the start of the project. Engineers have been combining these systems for the past 30 years. Many professionals naturally designed mechatronic products long before the field was formally recognized. The formalization of this practice traces back to the early 1980s. The turning point was the commercial arrival of the cost-effective microprocessor. Once engineers cheaply embedded processing power directly onto hardware, engineering design constraints shifted. Today, that growth is sustained by the ongoing information technology revolution, rapid advances in wireless communication, and embedded systems engineering. The hardware driving this forward is heavily reliant on MEMS technology. MEMS, or microelectromechanical systems, are microscopic devices that integrate mechanical and electrical components on a single silicon chip, enabling advanced smart sensors. As the performance-to-cost ratio of microprocessors and MEMS sensors increased, mechatronics moved from an academic theory into a standard requirement for modern manufacturing. Based on the level of integration between physical parts and computing power, all mechatronic products fall into one of four distinct classes. Class 1 consists of mechanical products where electronics are added to enhance an existing physical function. Examples of Class 1 include variable speed drives and NC machine tools. NC, or numerical control, refers to the automated control of machining tools via programmed commands, updating a physical machine with digital instructions. Class 2 involves mechanical systems with updated internal electronics, while the external user interface remains unaltered. Automated manufacturing lines and modern sewing machines fall into this category. Class 3 systems retain the functionality of their traditional mechanical predecessors, but their internal physical mechanisms are replaced by electronic components. The digital watch is the definitive Class 3 system. It tracks time like an analog watch, but the physical mainspring and gears are replaced by a quartz crystal and digital logic. Class 4 products are conceived from the start with mechanical and electronic technologies integrated synergistically. Intelligent washers, rice cookers, and automatic photocopiers are Class 4 systems. They require sensors, software, and moving physical parts to function as a single unit. The move from Class 1 to Class 4 documents the shift from treating electronics as a mechanical add-on to treating the machine as a cyber-physical entity. This mind map outlines the specific architecture required to build those systems. The study of mechatronics is divided into 5 distinct areas of specialty. Focusing on the top center node, the first element is physical system modeling. This requires calculating mechanics of solids, translational and rotational systems, and tracking fluid, thermal, and electrical dynamics. This list includes rotational electromagnetic MEMS, as physical modeling now extends to microscopic levels. This detailed view of the left-hand node outlines the second element, sensors and actuators. The top half lists the input devices required to measure the environment, including linear and rotational sensors, acceleration sensors, force and torque measurements, flow sensors, and vision systems. Once the environment is measured, the system uses actuators to move. These include electromechanical actuators, DC, AC, and stepper motors, alongside piezoelectric, pneumatic, and hydraulic systems. Elements 1 and 2 establish the physical constraints, dictating what the machine can endure and how much force it can exert on its environment. Looking at the right-hand node of the schematic, we move to the intangible logic that governs that hardware. Element 3 is signals and systems. This area relies on mathematical methodologies, including root-locust methods, state variable methods, and frequency response analysis to maintain system stability. It also incorporates advanced control designs like neural networks, fuzzy systems, and Kalman filters. A Kalman filter is an algorithm that uses a series of measurements over time to estimate unknown variables, which is vital for dealing with sensor noise. Directing your attention to the bottom right node, we find Element 4, Computers and Logic Systems. This covers the digital brain. It requires digital logic, communication systems, fault detection, and programmable logic controllers, or PLCs. PLCs are ruggedized computers adapted specifically for industrial manufacturing processes. The final piece is software and data acquisition, listed in the bottom left node. This acts as the translation layer, handling signal conditioning and relying on AD and DA, or analog to digital and digital to analog conversion. These three domains, signals, computer logic, and data software, process the raw input from the sensors and calculate the precise mathematical response required from the mechanical actuators. The evolution of the automobile provides a historical record of these 5 elements gradually integrating to move vehicles from Class 1 to Class 4 systems. Until the 1960s, a car was almost entirely physical. Aside from basic electrical loops, the dashboard radio was the only significant electronics in the vehicle. When occupant safety systems like seatbelts were introduced in the early 60s, they were entirely mechanically actuated. Engine control was similarly rigid. A mechanical distributor selected spark plugs based on engine rotation. While functional, it was inefficient for fuel consumption. In the late 1970s, the electronic ignition arrived, representing one of the first true mechatronic systems in automotive design. Instead of a physical distributor, the system used dedicated microcontrollers. It pulled data from airflow sensors and Hall effect sensors to time the spark ignition, which detect magnetic fields to measure the position of the crankshaft and camshaft based on load and speed. During this same period, the anti-lock brake system, or ABS, was introduced. ABS uses sensors to detect wheel lockup and then mathematically modulates the hydraulic pressure to prevent sliding. By the mid-1990s, this evolved into the traction control system. TCS senses slippage during acceleration and modulates power to the wheel to maintain acceleration under poor road conditions. In the late 1990s, Vehicle Dynamics Control augmented the TCS by adding yaw rate sensors and lateral accelerometers to track the vehicle's physical orientation. Modern standards use integrated radar systems to continuously measure range and velocity, allowing the vehicle to autonomously maintain a safe distance from other cars. Modern vehicles operate through a continuous millisecond by millisecond feedback loop between physical modeling, sensors, logic controllers, and software. Looking at the complete map of these intersecting disciplines reveals the complexity required to build modern technology. Because engineering boundaries are no longer clearly defined, designing a product strictly through a mechanical lens is impossible. Engineers require a multidisciplinary education to contribute to these systems. The future growth of this field is dependent on a specific set of enabling technologies. This includes the continued advancement of cost-effective microcontrollers and the expansion of MEMS applications for smaller, more accurate sensors. It also requires the maturation of adaptive control methodologies, real-time programming methods, and the integration of wireless networking. Finally, it relies on mature CAE technologies. CAE, or Computer-Aided Engineering, uses specialized software to simulate advanced system modeling and virtual prototyping, allowing engineers to test mechatronic designs before a physical part is manufactured. This structure represents the current standard for modern engineering design.